Well, thank all of you for joining us for this webinar hosted by the Center for Advanced Transportation Mobility, or as we also call it, CATM. I'd like to welcome Dr. Hyoshin John Park from North Carolina Agricultural and Technical State University as our presenter today. Dr. Park is an assistant professor in the Computational Science and Engineering Department here at A&T. His research focuses primarily on the optimization of transportation systems. He has several projects funded through CATM and other organizations outside of the UTC program. Today, he will discuss a few of these projects under the umbrella title, Collaborative Multimodal Decision-Making with Advanced Transportation Technologies and Computing. Dr. Park, welcome, and the floor is yours.
Hello, everyone. My name is John Park. First, I appreciate Miranda for at the start of this project. It was initiated by a couple of CATM projects, and then I will show you in a second, but there are multiple projects. So keep in mind that I may not go into too much detail during the presentation within 15 minutes to an hour. So please follow up with me through the email if you're interested in any of the project or paper. So to begin with, I would like to appreciate my collaborators. I have following students from A&T, collaborators from Embry-Riddle and Virginia Tech, and NASA JPL, and also NC State University. So it was a little bit challenging to group all of them together, but let me start with the motivation of the whole project in common is it's a predictive decision making. So if you search for dynamic programming in general, we have a dynamic decisions in a sequence. In addition to that, what I'm doing is I'm trying to model what's going to happen in the future analytically. And when I make a decision for now, I'm considering that future decision. So it's more like anticipatory decision making. And it was awarded as a patent in the transportation infrastructure, sensor location and deployment problems in connected vehicle. And this has been leveraged to the multiple problems. And since 2018 until now, past 3 years, I could group these ideas and projects into 3 themes. So first is for an active sensing, so you're making a decision of where to go. So it's sensors are actively locating to different locations through autonomous vehicles on the air. So I will introduce the theme 1. Theme 2 is pedestrians, vulnerable road users are making decisions to where to go in the building or outside of the building to catch a bus. And theme 3 is making a decision which vehicle, which public transportation or paratransit to take, or how their paratransit operations are going, or which route I want to take, or depending on the departure time when I'm driving myself. So all these projects have common themes originated from, if you see the center, dynamic sensor deployment, dynamic programming, dynamic decision making, on the uncertainty when there's adaptive routing and information gain. We try to maximize the information gain throughout the routing by considering some unexpected situations. So routing has to be adaptive, really adjust. And also that's a theme 1, theme 2, and theme 3. Traveler, they have their own rationality to maximize their own utilities. So these are analytically modeled, and these are in the theme 2 and theme 3. So I will start with the emergency response problem. So I have it's not within this presentation, but I try to find the interrelationships between the events and then model what's going to happen in the future. Based on that, I'm trying to make a decision of which emergency vehicle to be dispatched at which location. When we do that, this is a system level decision making to maximize the benefits to the system. And also another consideration was, so I tried to have this, and this was funded by the CAREM project, how we consider the traveler's rationality, and also based on that as an input, we make a better system decision making. So how traveler, when there is an incident, how they make a decisions differently. So I put this as a theme 3, and I will also gonna be ending with theme 3 in the different project. But this one is specifically looking for how different rationality will change, and based on that rationality, how we can make a different decisions for emergency vehicles. So I think I introduced how we make a decision considering the future occurrence of events. So let's say you have between 7 and 8, there are 3 emergencies, and the emergencies are occurring in a sequence, and you have 2 emergency vehicles, A and B. So in general, in the literature I'm currently in operation, no matter what probability is expected in the future, you just assign the nearest emergency vehicle to the site. That's in general what's happening now. But instead, if you have 3 emergencies are averaging occurring in a sequence during the rush hour, that's actually it's 8 average in Maryland. So in that case, you have a limited emergency vehicle, how are you gonna dispatch? So instead of just putting the A to, so instead of putting A to the nearest one, how about putting assigning the A vehicle to the first emergency at 7. So this is, again, this is, I'm not gonna go into detail, but this is more predictive decision making that I will list this in the paper later. So considering this, how people actually, when there is an emergency, you're driving on the road, and usually there is no congestion, but you see there is a severe congestion now. You could have an experience in the previous time or not, based on that, how they're gonna make a decision. So based on that, I try to simulate in the transmodeler, and also sometimes because the clearance duration is very long, how sometimes the emergency vehicle is not available in the next stage. So I'm also considering the availability of the resources in the future. So there are 3 things: the traveler rationality, available emergency vehicles in the future, and then the network congestion level. So we want to minimize the total delay caused by incident by responding to the incident very fast. So another example here is when you have ABC let's say these grid cells, if shaded shell is there, and if in the past historical data, if there was an instant on that location, somehow the instant duration was more than 30 minutes. And if instances are occurring every 30 minutes, then the next instance, any emergency occurring there, if emergency vehicle is respond to that location, is not going to be available. So see, the B was responding to the first instant one here as a star, and then C is going to respond to the second instant. However, it's not going to be available for the next stage. So we have to consider, that's what I was considering in the decision-making model. And the A is responded to 4, 5, 6. So now, instead of just making the best decision in the first stage, if you can simulate all of these, now you see 6, and I want to have a best benefit of accumulative of over these 6 assignments by using these 3 emergency vehicles. And this has been integrated with, this is algorithm integrated with multivariate utility function. In the mixed logic model, how probability of choosing route for each individual travelers can be changing. So let's say if in this freeway, people are driving, I just the one person let in my colleague from NCDOT. So how people are going to exit, or they're gonna just decide to stay on the road based on different scenarios. So that has been simulated in the transmodular environment. And the logic model has been the input to simulate the behavior of the traveler's choice. So based on that, I could come up with a better decision making for how we can minimize the delay caused by incident by allocating a better emergency vehicle for different locations. So so that is the first one. Then so every project is interrelated. That's why I try to have that category of the projects. So now we have drones on the sky. Actually, can find the 3 things and give a very variable information to the emergency vehicles. So we can find the better route by putting the UAV in the different locations, which is a better locations. For example, emergency vehicles, typically they cannot go maximum speed on the shoulder range when there is a disabled vehicles is expected. So this machine vision from UAV can find any potential disabled vehicles. If there is none, then can let the emergency vehicle know, so the emergency vehicle can go maximum speed. And also currently UAVs has been just assigned to the instance scene to see the progress of the clearance. Or there's more useful information, harder to catch in reality. So this project has been in collaboration with Virginia Tech, and then the Virginia DOT is supporting to the real world traffic capturing. So we are trying to have a use case on there is a shock wave caused by the lane blockage, and the shock wave is moving in real time. So how we can capture actually for that, and then we have a different benefits by looking at the shock wave. Maybe shock wave is not a big deal, or it could be a big deal. So we have now the problem is you have 2 emergency vehicles and you have 2 drones, and you are making a decision of assigning these 4 units. So how we can do that? So that is the drone team project that is going to finish in spring semester. And then we got, so this is an example case. You can see the ERB, emergency response vehicle 1, 2, 3. They're gonna assign to the star 1, 2, 3 emergencies based on how UAVs can, what kind of information can get. And so based on this example scenario, the ERB is assigned to the first one, and then the third one. The first one, the fourth UAV is gonna go to find there's no disabled vehicles on the road. So every information is quantified and then evaluated, and we are trying to maximize the gain from this information as a delay in the emergencies. So I could say I tried to have a different size of the network, simplified in the grid, 10 by 10 to 500 by 500. And compared to the previous literature, we could have a significant benefit in reducing not just the response time, but the delay as well. So we got lucky this idea. Also, at the same time, I was trying to get multiple projects with the same idea, similar idea, how in general, theoretically, the UAV can guide the ground vehicles, and then how they can cooperate. And so I'm not a Mars person, but I got good collaborators and I got the data. So basically, it's the same, similar type, not in the emergency environment, but it's a typical, it can be a traffic too when there is an emergency. But in general, when you have a ground vehicle only, and the ground vehicle has a limitation. For example, in the Walmart, they have a delivery vehicle. And in general, we know the surface type and surface, how the traversability of this small delivery vehicle can go up and down. However, there are some circumstances that uncertainty comes in. It's rainy or there are too much traffic. So UAS or camera can actually give information to that. And then by having more information theoretic and with the strategy of optimization, we could come out with a better route for both the ground vehicle and the UAV. So this has been ongoing project by NSF Robust Intelligence Program. And then this one also got a good application to the hurricane environment. So when you see this inside is the eye of the hurricane. And in general, the NOAA and in the typical situation, you just drop the drone inside of the eye of the hurricane, whatever, and then you get just to get some of the data, transmit to the mothership, and then just the drone just dies. However, it's the same logic. We can maximize an information of the whatever drone is getting about the hurricane. We try to go to the locations where the uncertainty is highest, and then visit multiple locations using the multiple drones with the multiple aircrafts, and then we can maximize the information so we can reduce the uncertainty. And behind this is there is a model for the track and other system models, and then we get the errors from that. So it's in the loop that we get a feedback. By doing this, we get an improvement in the system, and then based on the feedback, we try to improve our strategy for different routes. So So this has been the first theme of how we collaborate the UAV with the ground vehicle, so that I have the ground vehicle routing, but that can be improved even better with aerial vehicle. So in this second theme, it's still a routing problem, but it's for the pedestrian. It can be outside or inside, outside in the sidewalk to catch a bus, or inside of the building to evacuate. So in general, if you have been in San Francisco, I just I'm so tired of all day walking, and then I see that uphill that actually I didn't know, and then to catch my bus, I have to go all the way down, up and down the uphill. However, maybe fine for me, but however, some vulnerable road users, it can be just older elderly person or physical disability or any kind of just the tiredness or anything. So how about considering this the sidewalk conditions when we give the route decisions for travelers? So in general, the Google Map, so first left hand side is if you go to Go Triangle in North Carolina, it's gonna give you a trip planner to catch which bus to take. The second one is the Google, and the third one is Massachusetts. So first the two, if you put the wheelchair option, sometimes some cities will have the wheelchair user option, but that's not completely integrated with the bus situation. So it's not really wheelchair user can use this. The third one is integrating, but it's more toward the static model that cannot adapt to sometimes the wheelchair user cannot go through some construction, or if the road is broken, uh, it's not traversable. So how we can accommodate this uncertain and dynamic situation in this the trip planner. So, so this is another example how why the current the commercial trip planner cannot accommodate the situation I'm talking about. So let's say you are going from A to B, from the right hand side to the left hand side. You have multiple options. What you could do is you could just to take that there is, let's say first it's rainy, and there's a high slope and there's a walkable option. So you can actually try to take the high slope, or just to if you are running late for your catching your bus, you want to take a shortcut, then probably you just you don't want to take a detour. And also there is in this middle, there is the construction that actually you didn't know at the beginning, but you found that you have to take a detour. So how this wheelchair accessible, or it's more accommodating this kind of adaptive trip planning can be made. So we fortunately we could find the sidewalk conditions in Boston network, and then we applied our model. So again, there is a static parameters, sidewalk width and length and surface and the elevation, they do change. We didn't consider in here as the rain and the snow as a changing factor, but it can be dynamic too. However, we consider the construction as a different factor. Oh, so actually, when it's snowing, the importance of the surface will change. So it has to be also considered in there. So so that is why I consider the rain, although it's not dynamic, currently it's static. However, the the construction is unknown, and it will change our decision based on the situation. So I try to compare if we just find the shortest path, and then if there is on construction later on the trip, or if there is static minimum cost, we still consider all these utilities, but we are trying to just to consider everything is static. So it still have a problem when there is a construction. And the dynamic minimum cost and dynamic adaptive are what we are proposing. So I could see, we found that in different situations, this was when it's snowing, but sunny and rainy in different circumstances, we could find always having this adaptive model behaves the best. And this, I think a previous one also, I think the last slide, I listed all of these papers, so you can contact me or you can find from the journal. But this has been, it will be presented in TRB 2021 in January soon. So for more details, you can attend the conference, the presentation. So, so that has been on the sidewalk routing. And this, however, that doesn't directly apply to the evacuation in the building. When 50 pedestrians are trying to evacuate when there is an active shooter in the airport, everyone will try to go whatever they think the best. So there is more called social force model considering the pedestrian dynamics developed by Embry-Riddle University, Aeronautical University. So they try to come up with that, and then using that as an input, we could simulate when there is an entrance and exit, how people will try to evacuate. And then we simulated that and we got a density map. And then using that as an input, we found a better route for some of the designated people to go to different route. So think about situation, there is an evacuation, there are 50 people. We have some limited security people, so we are rerouting some of the people to the designated route on the corner, and there's going to be the traffic horns for people to follow. So but how we find that a designated route while there is still this social force model based just naturalistic evacuation model. So we found this density map by running the any logic simulation and using the social force model as an input. And this as an input, we found if you applied in the airport simplified situation where you have multiple obstacles, and then you found we have this optimally guided path. And then we have different scenarios when we have a different ratio of putting the pedestrians, more people toward this optimally guided path. Right now it's a simple one path, but it can be multiple paths in the future. So this is a simulation of the blue one is guided path. You can see, so actually when we just have all yellow, which is social force based model, we are not going, let me let a person in. Yeah, so we compared this simulation. If you have a baseline example where there is no blue optimally guided path people, it was much longer evacuation time. And by putting 25 to that designated optimal path, we could save 10 seconds of evacuation time, which is significant. Every second in the building evacuation will count. So, this is currently under revision, but please, if you're interested, please follow up with me. I can share the PDF of the journal, the paper. So I hope you still remember what happened in the pedestrian sidewalk model. So if you think about you are in San Francisco, you are deciding which bus to take, and that has a slope, to catch the bus, but bus also has some uncertainty in the on-transit time because of the congestion going through some congested areas. And then I don't want to stay, say I could be happy being in the San Francisco, but I don't want to go through this traffic. Everyone will have a different utilities and preference. So how we can accommodate this when I make a decision, it's not just the sidewalk, but also different bus route and schedule will have different utilities for me based on the uncertainty. And I could be very reluctant to this kind of uncertainty. I just want to go to the route that has no uncertainty, but it takes longer time. Or it has some uncertainty, it's going shorter route, but may have a congestion based on the history. So that has been modeled as it's called, so previous one was VRU pod, this is a VRU top. It's considering the traffic optimization. So how we can model that, how we can actually consider the traveler's utility based on the uncertainty of the travel time. And then that uncertainty will change based on the coefficient for each travelers. So we can change that and then we can find a better decision making. So this also has been accepted for presentation at TRB 2021. So please follow up with me, or you can see the last slide of this presentation. It has the link of that. So, and also it's under revision. So it's under review for a paper, so I can share the paper too if you're interested. But basically, this traveler's utility is changing based on the uncertainty. Here is a standard deviation of the travel time of each route of the bus, how we can consider that. And also previously the sidewalk condition is an input to that, how that can change the choice of in the trip planner, which bus to take can change. And this will be different from the Google map because it will consider my own preference and consider more the user-based, so it can be more preferable for the users too. So so this got a good potential, so we could actually extend this as currently ongoing as a matching project by NCDOT. So North Carolina, if you know, we are going through Medicaid transformation, which means previously the transit authorities have their fund to allocate the vehicles to pick up and drop off patients to the hospital. However, from now, these people, so to us, there's no change, but this has been, there's a privatization. So this fund will go to the hospital. They will find some Uber driver to pick up somebody and then drop off at the hospital or the other way. So this will cause, we don't know, we are looking at it, but it's the same framework as the VRU top, the same problem but different angle. So how this maybe, and we are looking at in different situations, sometimes when there is driver, Uber driver who is not familiar with the area, picking up a patient. However, he never been there, so he's looking for the area. So that will cause some of the delays in the pickup time. So when you schedule multiple pickups and drop-offs, you have to consider this time window of waiting time or delay in the picking up. If that is zero, great. We can just optimize putting the zero pickup time. But we have to know, we have to model that so that we can actually make a decision making. So going to the first question, when I started with, I'm trying to model this, the system, what is causing the delay. So I'm considering this as an input when I optimize how we schedule the drop-off and pick-up the customers. And then I could find some of the interactions still ongoing, but there are some interactions in the previous data that if it's nighttime, it's very suburban area, picking a customer from home, there is more delay compared to if it's in a return trip, the patient is going home, the picking up from the hospital, the Uber driver is well known. So this will be significant the factor for this problem. So this is an ongoing project in collaboration with NC State. So this is the last group of the problem. Originally, I used the choice model to find how people are choosing their route or switching their route when there's an emergency. So there was a rather naive model, but we expanded that to also supported by NCDOT ongoing for now. How about, so if we can, it's not just to rationality. How about we are letting some of the people, okay, you can take this route, it's shorter. Actually, when you use the Waze or Google Map, it always tell you there is a shorter route, you want to take it. But however, that is based on just to the travel time of the route at that time. It's not considering if you change, everyone else changes the route and go to the same route. It's happening to me all the times that I want to take a shorter route and everyone has the same decision. I'm stuck. It takes actually longer time. So how that is gonna impact? How about if you're not gonna tell everyone to change, but you may through the connected vehicle technology, you may find the 20% of the users to go to the specific route, considering other people will make their own decisions. So it's beyond the dynamic traffic assignment problem. It has to also consider the memory of yesterday's decision impacting on today, how this everyday decision or within day decision can be considered. So you can see the upper one is showing that there is, I think this is the same thing I was explaining for the transit route. The upper one is 8 minutes, and it's just the route that I usually go. But the bottom one is the 6 minutes, and it's shorter, but actually it could take 5 more minutes. So at the end, it may take up to 11 minutes. If I just stay on the road, it could take less than 9 minutes. So should I take a risk or not take a risk? And how many percent of people changing this based on their rationality will have an impact on the transportation network. So that has been the problem. And we have the informed decision making, uninformed decision making. People simulated by using the usual equilibrium, and everything was considered. Also, the rationality of switching the threshold based on the bottom figure is about the perceived travel time keep changing based on the within day and day-to-day time window. So we could find actually just having 20% of informed people could actually save a lot of travel time, travel delay on a congested network. And it will take some time to go up to 80% informed people because people may not follow. But just having this 20% by using the current technology of the connected vehicle, it can actually save significant. So in here, it could reduce up to 12 minutes. It could be significant if its total time could be 20 minutes of the travel time. So we try to see each path in different departure time and how their delays are changing when we consider not just the dynamic user equilibrium, it's a DUE. If you consider dynamic system optimum delays, which is our model can minimize the congestion much better. So that has been my research on the past. So this will be also in the TRB 2021 annual meeting. So you can follow up with the presentation conference at the end of January. So this all has been in this 13, so one patent, 2 book chapters, and 7 journals has been published, conditional accepted or revision, and the 3 are under review. So all of this, you can follow me after the meeting and we can talk. And also there are 3 more than 30 conference papers as intermediate progress of each of the projects that was published or presented in the papers in the below. So you may find the papers by just going to TRB 2020, or some of them are under review, has not been published yet. So you can talk to me and we can find a way to share this project. So I tried to finish in 45 minutes to put some time for the questions. So let me know if you have any questions.
Thank you, John. You definitely had a lot of information provided through these presentations. So we'll open up the floor and see if there are any questions from the audience. Okay, I have one question I did want to ask. You covered projects that actually spanned from pedestrian, highway, in terms of emergency use, hurricane, mobility challenged individuals, healthcare. In terms of the short term, I guess, impact of your studies, can you explain a little bit of what you envision to be the short-term impact of the results that you found thus far? I know some of your studies are still ongoing, but how do you see the results being implemented into practice?
Yeah, I think, let me go to, yeah, so I think I can explain for each theme. First, the theme is I'm not sure how much of the short term, but currently North Carolina is going through the automated technology for emergency response. So the in the previous times, when I go to this emergency day of the ITS America, where all these emergency dispatchers are in the room, we talk to them. It's very hard to talk to them because they're just driving what they're assigned to. However, we are developing this technology so that it could just not a driver of autonomous vehicle going to the site, or it's automated dispatching system. It could be there is a person in the car, but this dispatching will be automated. So in the short term, I'm currently trying to pitch and talking to the local agencies if this can be applied to that automated dispatching technology. So this AI decision making, which was very hard to follow in the previous people to train each dispatcher. You're telling the dispatcher, okay, you're done, you go to the next, which will be very, very hard. But now that will be just in the AI having just to make a automated decision. They may follow more easily with the vehicle technologies. So that is for example, also the hurricane, which is not actually the transportation field, but that is also actually people are dropping the drone inside of hurricane eyes. It can be just to be modified the routing algorithm to go to a better route. So because as the core idea of the theme one is to find a better route, any technology in place coming in a short, in a couple of years, it's implementable. So, but it's just based on the priority of the state fund to which case scenario is more important. So pedestrian navigation, it's a little bit more difficult to find the build on map because North Carolina, for example, doesn't have. I had to follow the map from the Boston, but not every state has the sidewalk condition. So that will we have to build a map, and then for implementation, that will be a challenging task. But considering we have a map, the routing itself is not a very difficult task. Evacuation, currently, I think that there is a path, optimized path, guided path for some of the evacuation. In the evacuation scenario, some of the pedestrians will be guided, but that's not based on the optimization. That's just based on the evacuation plan. So I think that's also implementable. The benefit of that, when there is actually an active shooter and there's a significant casualty, I think, and also right now there's a COVID-19, or considering all this complexity, I think it's a big problem. To answer your question of implementable right today in the short term, I think there are some challenges. First, in finding the sidewalk map, which is actually, I'm working with NASA. They actually have the traversability map, but which we require to convert into the sidewalk map. But there was a project by NASA already, which we need to convert it to the North Carolina, the GIS network. The theme 3, I think the first idea of the informed driver decision making, considering the connected vehicle technology is coming, already a lot of them are connected. I think we can have a significant benefit. It will require some real world testing though, but based on our realistic simulation, it's showing very significant. Um, the it's just much better than not doing so. But it's based on how much of this congestion mitigation and removing the delay per user will be prioritized over other projects. And the last mile project that is also very implementable that I'm hoping for. Right now, the project itself is just for finding what is causing the delay for the paratransit in this privatization situation. But however, and also actually the VRU top project is actually developing the better operation model. So yeah, actually can apply it, but it also has some barrier of it can be simulated, but in the real world implementation of changing the bus route, I think it could be easier for this paratransit, but the fixed bus requires the public hearings and that kind of more rigorous, more challenges to change that. But for just suggesting a better route based on, I mean, we're gonna have the better route and schedule for the public, the paratransit. So implementing that and comparing against the base model, I think it's very promising. So it can be more short-term project. Hope I answered your question.
Yes, it was kind of a loaded question, I see, but thank you. Yes, just to kind of get an idea of where these things will be going in the future, near or long term. I specifically asked for more the short term, just to get an idea of which ones are applicable relatively soon, or will be able to be applied relatively soon.
Thank you for the question.
Mm-hmm. Any questions, any additional questions from the audience?
I had one quick question. Can we go?
Yeah.
Okay. Thanks, John. Yeah, I really love the big picture themes and the graphics. I'd like one very specific question, maybe, but it was related to the IdeaNet, the theme, where you were talking about like when there are uncertainties that are associated with the routing component. I'm curious, like, are you also looking at the evolution of the routes from one day to the other? So is it?
Give me a second.
Yeah, so yeah, the slide.
The evolution from one route to another.
Yeah, so when I see the day axis, I'm curious, like, are you looking at the evolution of the routes that the travelers choose on a particular day, from that to what the routes will be on the next day? So it's like a day-to-day evolution is what is that?
Yeah, actually, yes. So let's say, so we consider both the within day in different time of day based on the traffic congestion will change. But day to day, for example, the memory of the traffic congestion caused by accident yesterday will be still in my mind when I'm driving the same road. So that was considered here. So we call the within day, day to day, the traffic assignment model. We both for the informed and uninformed. I mean, we cannot really inform the people. So the informed decision making for the day-to-day changes is less, but however, it's a lot. So let me say again. So although the informed decision making will change a lot of delay today, it will change tomorrow too, because the history of that memory in my mind will be there. So and that impact will be reduced by time goes on. Yeah.
Yeah, I think that's a very interesting component because like, especially like usually we are interested in like a long-term steady state, but the evolution from day to day is something. And then that's what I was curious, like in this graph, you would expect that like from day to day, the costs will lower and kind of stabilize to a low, sort of a low.
Right. There's that. Yes. I think I couldn't, I tried to cut everything here.
Definitely, but yeah.
Yeah. But I think I do have that graph too. So, yeah, I think it's gonna be in the TRB 2021.
Okay, I can follow up with you later.
Yeah. Larkin for some is in this meeting and he's gonna be the presenter. And it was from his dissertation, so I think he will have more details on that.
Okay, perfect. Yeah, I'll follow up.
Thank you.
Any more questions? I think we still have time for at least for one more. We're about at our time. All right, Dr. Park, did you have anything else you wanted to add?
Well, I think that's it. But thank you for your time, and hopefully we have follow-up discussions.
Thank you. Thank all of you for attending the presentation. As you can see, Dr.